In this video we are going to look at vectors and recall how we add vectors, how we multiply them by a scalar, how we use a coordinate system to assign coordinates to a vector, and also how to compute its length, and the basis vectors that will be often used during the course. So I remind you that a vector is nothing but a quantity with a magnitude, so a length, and a direction. So that's why we usually represent vectors by directed line segments, so little arrows. So the line segment going from point A to point B would be the vector AB. Where in the notation we put a little arrow on top of AB to indicate that we are talking about the vector. Since we only care about the direction and the length, if I were to shift this line segment over here to going from point C to point D, I would still get the same vector. So CD in this drawing is the same thing as AB, as the vector AB. Okay, so these two vectors are the same. Now you remember how we add, hopefully you remember how we add vectors. So vector addition is done using the parallelogram rule, where you take two vectors, let's call these A and B, you shift them so they have a common initial point, and what you do is form a parallelogram by shifting the vector B along the vector A and vice versa with the vector A along the vector B. This way you get this parallelogram, and the sum of these two vectors will have the same initial point and go to the opposite corner of the parallelogram. So that's the sum of the two vectors A and B. Now my first question to you is, well, take these two vectors, let's call this now A, and this vector B. So what's the sum of these two vectors? And you will have four options. So let's say option 1 is this vector, capital A. Option B is this vector, capital B. Option C is this vector, capital C. And option D would be, let's say, this vector, capital D. So which of these four is the sum of little a and little b? Pause the video and select your answer. Okay, so I hope you paused the video. Now if I do shift them to a common starting point, I would end up with this drawing, or I could also shift B to the end point of to start B, to have B starting point be the end point of A. Either way, the sum of the two vectors is this vector, which hopefully reminds you of capital B. So that was the correct answer. Okay, so now that we know how to add vectors, now we look at scalar multiplication. How we multiply vectors by numbers. So we can take a vector and multiply it by a number. For example, in this drawing, if I would want to multiply A by 2, that means I look at the vector that goes in the same direction but is twice as long as A. So that would be 2A. Okay, multiplying it by a positive number could either stretch the vector along its direction or shrink it. So if I were to take a half times A, then I would get a vector that is half as long as A, but still would point in the same direction. Okay, If I multiply the vector by 0, I get the 0 vector, which has no length or well-defined direction. And of course, we can multiply vectors by negative numbers. So for example, b over here multiplied by -1/3 would be a vector that points in the opposite direction than b, and its length is 1/3 of the length of b. Okay, so let me just say that for scalar multiplication, the length of c times a, where c is a real number, is the length of a multiplied by the absolute value of c. Okay, and the direction of c times a will depend on the sign of the number c. If c is positive, then c times a points in the same direction as a. If c is negative, it points in the opposite direction as a. Okay, and the length of a vector is of course just the distance between the initial and end point. And with this, we can turn to the components of a vector, which basically means putting vectors in a coordinate system. So just like we did before, we have a 3D coordinate system, and since the vector's initial point can be arbitrary, it might as well be the origin. So vectors starting from the origin are called position vectors because they basically point in certain positions in the plane. So if point P is the endpoint of our vector, then this is the position vector OP. And if the point has coordinates A, B, and C, then we say that the position vector OP has components A, B, and C. Okay, and notice the difference in notation with these angle brackets. I usually denote the components of vectors. So now if you have a vector pointing from point A to point B, so let's have this vector give this vector coordinates x1, y1, and z1, b x2, y2, and z2. Then the vector AB pointing from A to B will have components x2 minus x1, y2 minus y1, and z2 minus z1. Okay, and now that we have these components, these coordinates, we can turn these operations as vector addition and scalar multiplication into operations with numbers. Before doing that, let me just ask you a quick question. Question 2 is, what is the vector, the position vector that represents the vector pointing from A to B, where A is the point with coordinates 2, minus 3, and 4. That's the initial point, and the end point is B with coordinates minus 2, 1, and 1. Okay, so what is A, the position vector that is pointing from A to B? Okay, pause the video and input the components below. I hope you paused it. Now, if you compute these differences of coordinates, what you will get is, for the first component is minus 2, minus 2, that's minus 4. For the second component, you get 1 minus 3, that's plus 4. And for the third component, you have to take 1 and subtract 4 to get -3. So these are the components of this vector. All right, so now for my next question, let's just use components and practice a bit more. I'll give you two vectors with components. So vector A would have the components 4, 0, and 3, and vector B has the components -2, 1, and 5. And now I would like you to compute the length of A, the sum of A and B, the difference of A and B, 3 times B, as well as 2A plus 5B. Pause the video and input your answers below. Okay, I hope you paused it. Now for the length of A, clearly we just have to compute the length, the distance of this point from the origin. So that's just the usual Pythagorean formula with the square root of the squared sum of the components. So that's the square root of 4 squared plus 0 squared plus 3 squared. That's 16 plus 9, that is 25 under the square root. So we have for the length plus 5. Now if you add A and B, all you have to do is just add the components, corresponding components. So 4 plus -2 gives you 2 for the x component, 0 plus 1 gives you 1 for the y component, and 3 plus 5 gives you 8 for the z component. Now for the difference you do a similar thing, but you subtract the corresponding components. So from A, from 4, you have to subtract -2, so that gives you 6. 0 minus 1 is -1, and 3 minus 5 is -2. So this is the components, or these are the components of A minus B. 3 times B you get by multiplying each component of B by 3. So that's just -6, 3, and 15. And finally, to form this linear combination of 2A plus 5B, you multiply A by 2, B by 5, and then just add those multiples of A and B by component wise. So 2A plus 5B in the first component will give you 8 minus 10, that's -2. In the second component, 0 plus 5 will give you 5, and in the third component, 6 plus 25 will give you 31. So these are the answers to question 3. And finally, once you have components, you can talk about the basis vectors, and these vectors are vectors of unit length along the positive direction of coordinate axes. So let me just try to denote these unit vectors, indicate these unit vectors in this figure. So if I take the 3 vectors that point in the positive direction along the coordinate axes and have unit length, I get the basis vectors, which are called I, J, and K. Okay, so these are the basis vectors, and with these we can actually express any vector. So a vector with components, with 3 components, can be expressed as a linear combination of these 3 vectors. So for example, this vector OP can be expressed as, with components A, B, and C, can be expressed as A times I plus B times J plus C times K. Okay? So with this, we can actually reduce any vector into a linear combination of the basis vectors. And finally, if you want to form a unit vector from a vector that is non-zero, all you have to do is divide the vector by its length. That way you scale the vector down to unit length. Okay, I hope you enjoyed this video and I'll see you in the next one.